Down below here, we have a sketch of tangent x and cotangent x. Tan x is also the same thing as sin x divided by cosine x, while cotan x is going to be the reciprocal of this number. So while we'll only focus on sketching out the graph of tan x, a very similar idea can be applied to finding the graph of cotan x. And from the information that we've been given, we can see that tan x has a vertical asymptote when cosine x is equal to 0, and cosine x is equal to 0 when we have x is equal to pi divided by 2, or 3 pi divided by 2, and any multiples of these by pi. By the same logic, cotan x has vertical asymptotes when x is equal to pi plus n pi. Now let's focus on sketching the graph for cotan x. And recall again that y is equal to tan x is the same thing as saying that this is equal to sin x divided by cosine x. Unlike sine, cosine, cosecant, and secant, tangent and cotangent have a period of pi. Writing this using symbols, this is the same thing as saying tan evaluated at x plus pi is equal to tan x, and cotan evaluated at pi plus x is equal to cotan x. On the last slide, we saw that tan x has vertical asymptotes at x is equal to pi divided by 2 plus multiples of pi. So with the period being pi, and given that we know we have vertical asymptotes from pi divided by 2 and negative pi divided by 2, we only need to look at the behavior between these two asymptotes. Because again, the graph is going to repeat itself from negative infinity to infinity using this pattern. Now when we evaluate tan x at 0, we're going to get sin x is equal to 0 and cosine x is equal to 1. So tan x is going to contain that point 0, 0. As we approach the number x of pi over 2 from the left-hand side, our values of sine over x divided by cosine of x is going to approach 1 on top and 0 on the bottom. And furthermore, since our values of sine x are positive when we approach 1 and our values of cosine x are positive when we approach 0, then our values of tan x are also going to be positive. And so this is going to be a positive number that's growing exponentially large as we approach pi divided by 2 from the left-hand side, which means our graph looks something like this. Now, if we look at x is approaching negative pi divided by 2 from the right-hand side of tan x, then what we do know is sine x and cosine x is approaching negative 1 divided by 0. Now our negative 1, all our sine x values as we get close to it from the right-hand side are also negative, and our cosine x values are approaching 0, but all these are going to be positive numbers. So this means that tan x is going to be approaching a very large negative number. And so our graph will look like this. And since we found the shape of our graph on one complete period of tan x, we can go ahead and repeat this pattern for every period of length pi. The graph of cotan x will be left as an exercise for you to look at. Like the remainder of the trig functions, both tan and cotan can be transformed using specific transformations. These transformations are very predictable and can be represented using the regular form, which is given by the following functions. Again, here we have that A is a vertical stretch for each of these graphs. K is going to be a horizontal stretch or compression. And K again determines the period of our graph. And finally, H is going to be a horizontal shift of the graph. where again, if h is greater than 0, we shift right, and if h is less than 0, we shift left. An example of a right shift would be y is equal to cotan of x minus 1. An example of a left shift would be y is equal to cotan of x plus 10.